It turned out that what puzzled astronomers was not a single planet, but an entire class of worlds that seemed to defy every old pattern. We once believed that the universe would simply repeat the familiar order of the solar system: rocky planets close to their parent star, giant gas planets farther out, all moving along nearly circular, predictable orbits. Even theories of planetary formation reinforced that belief. Beyond the frost line, where temperatures are low enough for volatile compounds to freeze, giant gas planets were thought to be the only worlds capable of forming. Jupiter sits exactly in that region, and for a long time, we assumed every other planetary system must follow the same rule. But then, in 1995-51, Pegasi b appeared like a direct blow to that confidence. It orbits a sun-like star about 50 light-years away, and in nature it is a gas giant. The unacceptable part lay elsewhere. It is closer to its star than Mercury is to the Sun, completing one orbit in just over 4 days, with surface temperatures exceeding 1,000 degrees Celsius. According to every model at the time, such a world could not have formed there. Radiation from its parent star would have prevented the process, and the innermost region of the system simply did not contain enough material to build a giant gas planet. And yet, there it was, both absurd and real. From that moment on, astronomers were forced to consider another possibility. Perhaps these planets formed far away and then migrated inward. And alongside the question of how came an even more unsettling truth. 51 Pegasi b was not a rare accident. It opened the door to an entirely new class of planets, the hot Jupiters. And as observation technology improved, the number of such worlds kept rising. From the early 1990s to the present, we have confirmed more than 6,000 exoplanets, and that number seems to grow almost every week. What began as a slow trickle of discoveries has now become a flood of strange revelations. There are planets darker than coal, absorbing nearly every photon that strikes them. There are gas giants orbiting 2 stars at once. There are worlds that complete an entire year in less than 8 hours. And somewhere out there, there are storms that rain not water, but molten metal. WASP 76b is one example that makes the idea of hell feel chillingly concrete. About 640 light-years from Earth, this planet has a dayside hotter than 4,000 degrees Fahrenheit, enough for iron not only to melt but to vaporize. In its sky, there are clouds made of iron atoms in gaseous form. Because it is tidally locked, it always shows only one face to its star, much the way the moon always shows the same side to Earth. That creates one half of the planet permanently immersed in light and the other half trapped in eternal darkness. The temperature difference between the two hemispheres reaches about 1,000 degrees. The day side climbs to 2,400 degrees Celsius, while the night side falls to a cooler 1,500 degrees Celsius. That brutal thermal contrast drives winds of around 18,000 kilometers per hour across the boundary between light and dark. And then the truly bizarre happens. Iron vapor from the day side is swept over to the night side, where it cools, condenses, and falls as droplets of liquid iron, a kind of weather that works in only one direction, endlessly carrying molten metal from the bright side to the dark side of the planet. If iron rain is not enough to leave people stunned, then HD 189733b takes a different approach by deceiving with its appearance. It lies about 65 light-years away in the constellation Vulpecula. From a distance, it looks like a blue dot that could easily remind us of Earth itself. But that resemblance is entirely an illusion. That blue color does not come from oceans or life, but from silicate particles in the atmosphere, fragments of material that on Earth we would call glass. And beneath that beautiful blue lies a world with temperatures exceeding 1,000 degrees Celsius. There are worlds that do not die immediately, but clearly do not live in peace either. On HD 189733b, that blue color that seems so gentle from afar conceals a merciless weather machine. Winds there scream at about 7,000 kilometers per hour, 7 times the speed of sound. Under the extreme heat of the dayside, silicate particles are heated until they vaporize, Supersonic winds then sweep that vaporized material over to the night side, where it condenses. The result is glass rain. But even the way it falls is unlike any rain we know. Those shards of glass do not plunge straight down from above, but are slashed sideways through the atmosphere by winds so violent that even bullets seem tame by comparison. The very fact that planets like this remain intact is enough to force us to ask, how can they endure such radiation, tidal forces, and atmospheric chaos without being torn apart? The answer, sometimes, is that they do not truly survive. WASP 12b is the coldest example of that truth. About 600 light-years away in the constellation Auriga, this planet is slowly moving toward its end. It orbits its host star at such an extreme proximity that tidal forces do not merely affect it, they distort its very shape into something like an egg. The star's gravity does not simply pull WASP 12b inward, it swells the planet into enormous tidal bulges. At the same time, intense radiation heats its atmosphere until that gaseous layer expands beyond the limit the planet can still hold onto. Matter begins to leak into space, as if the world itself were bleeding into the void. Scientists estimate that WASP 12b may have only about 3 million years left. That sounds long, but on the timescale of the universe, it is almost a blink. We are witnessing a planet being gradually devoured by its own star, a death drawn out long enough for humans to recognize it as it happens. But not every strange exoplanet is a tragedy in progress. Some are not dying. They are simply so bizarre that they are almost hard to accept. TRES 2b is one of them, about 750 light-years from Earth. It holds the title of the darkest planet ever known. It reflects less than 1% of the light that falls on it. Coal reflects more. Black acrylic paint reflects more. This world swallows visible light with an efficiency that feels deeply unsettling, becoming darker than anything we have ever seen in the solar system. It orbits close to its host star and is heated to around 980 degrees Celsius, so reflective clouds like those on Jupiter or Saturn cannot form. But temperature alone is still not enough to explain it. The current hypothesis is that its atmosphere contains strong light-absorbing substances, possibly vaporized sodium, potassium, or gaseous titanium oxide. These compounds trap incoming photons and return almost none of them, turning the planet into a black hole for visible light. It does not vanish completely. Its heat still makes it glow with a dim red hue, like an ember buried in ash. But if you could somehow stand on its surface, there would be almost nothing left to see, because the world itself would have swallowed the light around you. Then, at the opposite extreme, the universe creates a complete counterpoint. LTT 9779b, about 260 light-years away, reflects as much as 80% of the light that strikes it, making it the most reflective planet ever discovered. A cosmic mirror hanging in space. The secret lies in clouds made of silicates and titanates. They act like billions of tiny mirrors, bouncing light back into space with astonishing efficiency. The irony is that this planet should not exist either. It orbits extremely close to its star, so close that stellar winds should have stripped away its atmosphere millions of years ago. And yet that atmosphere remains. One proposed explanation is that the metallic clouds are too heavy for stellar winds to carry off. The very material that makes it shine like a mirror may also be what protects it from being stripped bare. In a place like this, chemistry seems to have accidentally created an exception durable enough to resist destruction. And when absolute darkness stands face to face with near-perfect reflectivity, the next natural question is no longer what a planet looks like, but what it is made of. That is where the story leads to 55 Cancri E, a world often called by a name almost too beautiful to believe, the Diamond Planet. If there is any planet that instantly set the public imagination on fire, it is 55 Cancri E. Discovered in 2004, this world is a super-Earth orbiting a sun-like star about 40 light-years away. It has roughly 8 times Earth's mass and about twice its radius. But what truly sets it apart is not its size. Its host star is rich in carbon, and the planet most likely inherited that same chemical foundation. From its mass, radius, and the composition of its star, scientists once arrived at a startling conclusion. This could be a world made largely of crystallized carbon, not in the familiar form of carbon dioxide or organic matter, but as graphite and diamond. At least 1/3 of its mass may be pure diamond. With a surface temperature above 1,700 degrees Celsius, hot enough to melt iron, and a year lasting less than 18 hours, this planet appears like a colossal gemstone glowing red-hot in space. The idea of a diamond planet immediately seized the human imagination. But then science did what it so often does. It made the picture less certain. Some later studies suggested that 55 Cancri E may be richer in aluminum oxide, more like a sapphire world than a diamond one. Either way, it remains a planet not built from the familiar silicates of the rocky worlds in our solar system. It belongs to a different kind of matter, a different kind of planet. And then, before the question of composition had even settled, the universe moved on to challenge another rule: density. The Kepler 5.1 system, about 2,600 light-years away, contains 3 planets so bizarre that ordinary names hardly seem enough. They are called superpuffs, but cotton candy planets captures the feeling much better. They are nearly the size of Jupiter, yet their masses are only a few times that of Earth. Their densities are below 0.1 gram per cubic centimeter, so low that Saturn, the least dense planet in our solar system at about 0.69 gram per cubic centimeter, suddenly seems heavy. These worlds are lighter than foam. The current explanation is that they are wrapped in enormously swollen hydrogen and helium atmospheres that make up almost all of the planet's volume, while the solid core, if it truly exists, is only a tiny fraction. They are not like gas giants such as Jupiter in any way we once considered familiar. And here, once again, the problem appears. Such bloated atmospheres should be easy for radiation from the host star to erode over time, and yet they are still there. Perhaps it is because they are young on the timescale of the universe, and we are observing a brief phase before they slowly shrink into more ordinary planets. Or perhaps, more simply and more unsettlingly, we still do not understand how these worlds actually work. Some planets are not light, not carbon-rich, but instead exist in a state where chemistry is constantly being torn apart and rebuilt. Kelt 9b is an example so extreme it is almost hard to believe. It orbits its host star at a distance even closer than Mercury is to the Sun, and its dayside temperature reaches about 4,300 degrees Celsius, hotter than some stars. At that heat, hydrogen molecules are ripped apart into individual atoms. When the material flows to the night side, they recombine, only to be torn apart again when they return to the day side. The entire planet seems trapped in a permanent cycle of destruction and recreation at the molecular level, an atmosphere endlessly rewritten by its own temperature. WASP 107b offers a different kind of strangeness. It is about the size of Jupiter, but has only around 1/10 of Jupiter's mass. On this planet, the atmosphere shows an east-west asymmetry, meaning one edge of the atmosphere behaves very differently from the other. Our solar system has nothing like it. Its unusually bloated state and low gravity create conditions that we are still struggling to decipher. And then there is GJ 1132b, a rocky world that may have gone through a very different journey, losing its original atmosphere, then building a second one through volcanic outgassing. If this is confirmed, it would show that a planet can do more than lose the gaseous shell around it. It can also recreate it from scratch, a kind of rebirth on a planetary scale, a second chance for habitability. That may be the most haunting part of the entire story of exoplanets. Each time we discover a new world, what grows is not only the list of known planets, but also the number of unanswered questions. How do hot Jupiters drift so close to their stars without being destroyed? Why do some planets form metallic clouds while others absorb nearly all light? What determines whether a world will swell into something as light as cotton candy or be compressed into a strange mass of matter like diamond? The more we know, The farther away true understanding seems to recede, and the remarkable thing is, even at this point, we still have not yet reached the strangest worlds of all. The deeper I look into the universe, the more I feel that the familiar is what should make us suspicious. Planets orbiting dead stars, worlds moving along retrograde orbits, wanderers with not even a single star to call home, drifting through the emptiness between suns. All of it makes one thought hard to avoid. Perhaps strangeness does not lie in a few rare exceptions, but is instead the natural state of the universe. And our own solar system, with its neat arrangement and familiar planets, may be the true outlier. We built an entire theoretical framework from a sample size of exactly one, then acted surprised when reality refused to follow along. And what truly keeps astronomers awake at night may not be what they have already seen, but what they know they have not yet seen. More than 6,000 confirmed exoplanets sounds like an enormous number, but in truth it is only a tiny fragment of the full picture. The very ways we detect planets come with built-in bias from the start. These tools are not neutral witnesses. They were made by humans, and so they inevitably inherit very human assumptions about what a planet is supposed to look like. The transit method works beautifully, but only when a planet passes directly in front of its host star from our point of view. Tilt the angle even slightly, and the signal disappears. If someone were observing the solar system from some random direction in space, chances are they would never see Jupiter cross the face of the Sun, and so would never find it that way. The radial velocity method is more subtle, measuring the slight wobble a planet causes in its star. But small planets create only tiny wobbles. Earth-sized rocky worlds at comfortable distances almost vanish into background noise, unless we are extraordinarily lucky. Direct imaging, meanwhile, favors only planets that are large, bright, and far enough away not to be swallowed by the glare of their host star. The result is that we tend to see monsters lurking in the dark outskirts, while more ordinary worlds, if they exist, remain quietly hidden. From that, a profound selection bias emerges. We keep finding bizarre planets because our methods are best suited to finding the bizarre. PSR B 1257+12 was one of the earliest discoveries that should already have warned us that every safe prediction would eventually collapse. In January 1992, this system became the site of the first confirmed exoplanets. But what was shocking was not merely the first exoplanets. Those planets did not orbit a normal star, but a pulsar, a neutron star, the remnant of a dead star, spinning hundreds of times per second, and sweeping radiation into space with every rotation like a cosmic lighthouse. This is not a gentle environment. The very process that creates a neutron star, a supernova explosion, is so violent that it should blow away any planets orbiting it. And yet 3 worlds still exist there, discovered through tiny irregularities in the timing of the pulsar's radio signals. Among them, PSR B 1257+12b is so small it is almost hard to believe, only about twice the mass of the Moon, making it the lowest mass exoplanet ever discovered. Perhaps they did not truly survive the explosion. Perhaps they were born afterward, condensing from the debris thrown out when the star died. Second-generation planets, born from ashes, orbiting something that should no longer be capable of having offspring at all. Only about 0.5% of pulsars are thought to host planets, and the mechanism by which they form is still unclear. But the fact that they exist at all is enough to force us to rethink the limits of where a planet can be born and what catastrophes it can endure. Then there are worlds that do not orbit the remains of stars, but stars so small that, in theory, they should not be able to form giant planets at all. TOI 6894b, announced in June 2025, is one such example. It orbits a red dwarf only about 20% the size of the Sunday. Red dwarfs are the most common kind of star in the universe, making up about 70% of all stellar objects, smaller, cooler, and stingier with energy. And yet this planet is nearly the size of Jupiter. According to our best current models of planetary formation, that should not happen. A star that small is not supposed to have enough material in its protoplanetary disk to build a giant planet. The numbers do not add up. Physics seems not to allow it. But the planet is still there. LHS 3154b repeats the same defiance. A world 13 times the mass of Earth, orbiting a star far less massive than the Sunday. Such worlds continue to exist, as if they have no idea they are considered impossible. And so astronomers are being forced to revise the models in a hurry. Perhaps planet formation around red dwarfs is completely different from that around sun-like stars. Perhaps we have misunderstood how matter is distributed in protoplanetary disks. Perhaps planets migrate inward from distant orbits through mechanisms we have not yet imagined. Or perhaps, quite simply, our current theories are wrong at the root. But even then, the universe still has another way to push beyond the strange. 2M1510 ABB is a circumbinary planet, orbiting two central objects at once. That alone already places it in an extremely rare group, because only 16 circumbinary systems have been confirmed so far. But here, those central objects are not even true stars. They are brown dwarfs, failed stars that never gained enough mass to sustain nuclear fusion, existing in the blurred boundary between planet and star. A pair of brown dwarfs is already uncommon. A planet orbiting them is almost extraordinary. And this planet's orbit does not even lie in the ordinary plane. It follows a polar orbit, sweeping above and below the brown dwarf pair at a right angle to the plane in which they orbit each other. If you imagine the solar system having a planet that does not circle around the sun's equatorial plane but instead travels over its north and south poles, that is close to what is happening here. This is the first polar circumbinary planet ever discovered. From the moment humanity first observed protoplanetary disks arranged along polar planes, the idea of polar orbiting planets had already begun to take shape. But suspicion is one thing. Seeing a real world actually exist in such a structure is something else entirely. The discovery of such a planet confirms that planetary systems can organize themselves in ways far bolder than the neat diagrams we once took for granted. In a system where two brown dwarfs orbit each other, the gravitational field is never still. It shifts, overlaps, and changes constantly. And yet the planet still finds a stable path through that chaos, maintaining an orbit that simplified models can barely explain. That alone is enough to remind us that there are cosmic structures that function far better than our intuition would ever allow for. WASP 107b also belongs to the group of worlds that make intuition fail again and again. It is roughly the size of Jupiter, but its mass is so low that the entire planet seems inflated into a giant gas balloon balanced on the edge of stability. Its atmosphere extends so far outward that its density becomes strangely low, and detailed observations have revealed something even harder to understand: an east-west asymmetry in the atmosphere. One limb behaves completely differently from the other. Our solar system offers nothing like it. We do not yet truly understand why that phenomenon appears, nor do we know how such a fragile atmosphere has managed to withstand the stellar wind and radiation that should have stripped it away long ago. But that very extreme puffiness creates a rare opportunity. Light passes through the atmosphere more deeply than usual, leaving behind clearer spectral signatures, and because of that, we can analyze its chemical composition in greater detail, tracing how different layers of gas interact, circulate, and transform. The problem is that in exoplanet science, each answer rarely closes anything. It only opens more questions. GJ 1132b is another example, but this time what haunts us is not inflation, but the idea of a second life for an atmosphere. Early studies suggested that it began as a mini Neptune, a world wrapped in a thick hydrogen envelope. Then radiation from its host star stripped that atmosphere away, leaving behind what seemed to be nothing more than a barren planet. But the story may not end there. Volcanic outgassing may have built a new atmosphere, entirely different from the first. If this is confirmed, it would show that a planet can do more than lose its gaseous оболочка. It can replace that shell entirely over the course of its existence. Orbiting a red dwarf, a type of small, cool star with a lifespan stretching into the trillions of years, GJ 1132b, has immense spans of time in which to pass through multiple atmospheric stages. A world could move from hydrogen to carbon dioxide, then to nitrogen, as geological processes and the influence of its star repeatedly rewrite the layer surrounding it. Seen that way, planetary evolution is no longer a one-way path, leading either to habitability or to permanent desolation. A silent world may awaken again. A bare rock may regrow its sky. If GJ 1132b forces us to rethink how atmospheres change, then HR 5183b strikes directly at the concept of orbit itself. This planet is 3 times the mass of Jupiter and takes 74 years to complete one circuit around its star. But what makes it stand out is not that long period, but the shape of its orbit, an extremely stretched path, distorted to a degree that seems almost absurd. For most of its time, it drifts in the far reaches of its system, nearly motionless for decades. Then, at one moment, it comes hurtling inward at terrifying speed, sweeping close past its host star before being flung back out again into distant space. That extreme rhythm creates violent swings in temperature as the planet constantly shifts between the role of a frozen world and that of a scorched one. And there is more. Its orbit is retrograde relative to the star's rotation. That is something that almost directly defies the basic predictions of planetary formation theory, because a planet is supposed to inherit its direction of motion from the disk of gas and dust that formed it. HR 5183b's present orbit looks like a scar. It suggests that this system once went through some violent disruption, perhaps a close encounter with another planet, or perhaps a passing star that stirred everything up. Astronomers believe it is still migrating inward, and that over immense spans of time, tidal interactions will gradually circularize its orbit, turning this misaligned wanderer into a more familiar hot Jupiter. If that is true, then we are catching planetary migration in the middle of the process. WASP 12b does not have the luxury of millions of years of slow evolution like that. It has only about 3 million years left before it disappears. Orbiting far too close to its host star, it is being stretched and distorted into an egg shape by tidal forces, while intense radiation inflates its atmosphere, making the planet even more vulnerable. Its star is slowly feeding on matter from the outer layers of that atmosphere. And this is no longer a speculative scenario. The orbital decay of WASP 12b has been measured. It really is falling into its own star at a rate we can track. One day, astronomers of the future, if they still exist, will no longer see this planet. It will be vaporized, absorbed, erased from the sky, as though it had never been there. WASP 121b shows a different version of the same tragedy. It completes an orbit around its star in just over 24 hours and is tidally locked, with one face permanently turned toward the star and the other forever trapped in darkness. The temperature difference between the two hemispheres drives winds exceeding 16,000 kilometers per hour. The heat there is so extreme that iron, aluminum, and titanium no longer exist as metals in any familiar sense, but as gases in the atmosphere. From that arises a strange chemistry we can barely simulate in full. Ultra-hot Jupiters like this become natural atmospheric laboratories, operating under conditions humans cannot reproduce on Earth. But at the same time, they are also signs of the end stage. These are planets that have migrated too close to their stars, worlds entering their final agony, where their very existence turns into a prolonged process of self-destruction. There are planets torn apart when they venture too close to their stars. But there are also worlds that survive where survival should be impossible. LTT 9779b is one of them. It orbits its star even closer than many hot Jupiters already on their way to destruction, and by every ordinary line of reasoning, its atmosphere should have been stripped away by stellar winds long ago. And yet the planet not only still exists, it has become the most reflective world ever discovered. About 80% of the starlight that falls on it is thrown straight back into space by metallic clouds in its atmosphere. Those clouds are made of silicates and titanates, materials essentially akin to glass and titanium salts, enough to turn the planet's sky into a mirror. One explanation suggests that these metallic components are too heavy for stellar winds to blow away, while lighter elements gradually escape into space. What remains settles into durable cloud layers that both reflect fiercely and shield the gas below, a kind of atmospheric armor made of glass and metal. At the complete opposite extreme is TRES, 2b. If LTT 9779b is a mirror, then this world is more like an absence. It reflects less than 1% of the light that strikes it, darker than coal or black acrylic paint. Something in its atmosphere is holding on to nearly all incoming light. The prime suspects are vaporized sodium, potassium, and gaseous titanium oxide. In an environment hotter than 1,500 degrees Celsius, these substances exist as gases and absorb light across a wide range of wavelengths. TRES 2b emits only a faint red glow from its own heat, while reflection is almost negligible. These two planets stand at opposite ends of reflectivity. One is a mirror, the other a void, and neither of them fits the neat models we once believed were enough to explain planets. Perhaps that is the clearest recurring motif in exoplanet science. The universe has no interest in the simplicity of human diagrams. It only does what physics allows. Then there are worlds that go even further, planets that do not even bother to have a star at all. Rogue planets drift alone through the darkness between stars, with no dawn, no seasons, no cycle of day and night to hold on to, only an endless stretch of cold. The James Webb Space Telescope has found hundreds of such worlds in the Orion Nebula, free-floating objects not gravitationally bound to any star. That collides head-on with the standard model of planet formation, in which everything begins in a disk of material orbiting a young star. Remove the star, and the mechanism should disappear with it. And yet out there they remain, hundreds already revealed, and perhaps thousands more still undiscovered. Stranger still, around 80 of those orphaned worlds are not entirely alone. They move in pairs, two Jupiter mass objects orbiting one another as they wander through space together, a class of objects called GMBOs. Where they came from, how they were ejected from their original systems, and why they ended up locked into binary orbits with each other are questions science still cannot answer with confidence. Another rogue planet has been measured at a distance of about 9,950 light-years, with a mass around 70 times that of Earth. Human beings never saw it directly. We noticed it only when it passed in front of a distant star and bent the star's light. To determine its mass and distance from that event required coordination between ground-based telescopes and Gaia, now no longer operating. All that effort just to capture the trace of something almost invisible. And that, more than anything, is what is worth thinking about. If such nearly undetectable objects keep appearing, then perhaps the Milky Way contains billions of rogue planets. Some models even suggest that the number of wandering planets may exceed the number of stars. They have no star to reflect light from, nor any strong enough internal heat source to shine clearly in infrared. They are almost like ghosts moving through the dark. And when their numbers become too large to dismiss as exceptions, one question becomes impossib to avoid. Does a planet really have to belong to a star at all? PSR B 1257 plus 12b also does not orbit a normal star. It orbits a pulsar, and it was the first exoplanet ever discovered, in January 1992. That announcement changed astronomy forever. But what was astonishing was not merely the first exoplanet, it was where it was found. A pulsar is a neutron star, the collapsed core left behind when a massive star explodes as a supernova. These objects are so dense that a teaspoon of neutron star matter could weigh around 1 billion tons. They spin with extraordinary speed, sometimes hundreds of times per second, and emit beams of electromagnetic radiation from their magnetic poles, sweeping through space like lighthouse beams. To create such an object, a star must pass through a level of violence almost beyond imagination. The core collapses. The outer layers explode outward at a significant fraction of the speed of light. Temperatures rise into the billions of degrees, and the shockwave clears out everything nearby. Any planet that once orbited the original star should have been vaporized, destroyed, or hurled out of the system. And yet PSRB 1257 plus 12 still has 3 planets orbiting it. The most reasonable answer is that they did not survive the supernova at all. They formed afterward, from the very debris left behind by the star's death. Second-generation worlds, born from ashes, following a mechanism entirely different from the one that created Earth or Jupiter. This seems to happen only under very special circumstances. Only about 0.5% of pulsars are thought to host planets. For it to happen, enough debris must remain after the explosion. That material must settle into a disk, and that disk must stay stable long enough for planets to condense out of it. Most pulsars do not get that fragile chain of conditions, but the fact that even a few do is enough for the universe to prove that even after the most violent death of a star, planets can still appear one more time. There are discoveries that do more than simply add another planet to the growing list of known worlds. They force the entire field of astronomy to widen its notion of where planets can exist at all. PSRB 1257 plus 12b is one of those cases. It remains the lowest mass exoplanet ever discovered, so small that it is even smaller than our own moon. Finding such a tiny world was already astonishing, but the way humans detected it was even more remarkable. No one observed it directly. Instead, astronomers measured the arrival times of radio pulses from the pulsar with extraordinary precision. When a planet orbits a pulsar, its gravity causes the neutron star to wobble slightly, and that minute motion subtly shifts the timing of the pulses reaching Earth. From those almost unimaginable deviations, scientists inferred the planet's existence, along with its mass and orbit. This not only proved that planets can be found under extreme conditions, but also showed that they may form through pathways no one had truly considered before. Once we accept that worlds can exist around a pulsar, the question immediately expands outward. What other environments are we still underestimating? TOI 6894b is one example that makes that question feel urgent. This planet orbits a red dwarf only about 20% the size of the Sun, yet the planet itself is nearly as large as Jupiter. That combination alone is enough to crack the standard models of planet formation. Around such a small star, the protoplanetary disk should not contain enough gas and dust to build a giant world. The numbers simply do not work, and yet the planet exists. It was only announced in June 2025, and scientists are still trying to explain how a result that current theory cannot produce has appeared in reality. This is no longer a matter of one small detail drifting away from the model. It seems more likely that something is wrong with the foundation of our understanding itself. LHS 3154b reinforces that point in a different but equally uncomfortable way. It has 13 times Earth's mass, while the star it orbits is 9 times less massive than the Sunday. The star is too small. The planet is too large. That ratio, if we follow the standard theory, simply should not exist. And when cases like this begin to repeat, we can no longer keep treating them as lucky exceptions. Perhaps planet formation does not happen the way we once imagined. Perhaps there are still undiscovered mechanisms at work. Or perhaps the rules drawn from the solar system were never truly qualified to represent the rest of the galaxy in the first place. 2M1510 ABB pushes that feeling of impossibility one step further. Even its name carries something unusual. This is a circumbinary planet, orbiting 2 central objects at once. Although about half of the stars in the Milky Way exist in binary systems, having a planet circle both of them is still rare, with only 16 such systems confirmed so far. But this case is even more extraordinary, because the central pair are not ordinary stars, but 2 brown dwarfs, failed stars. that never gained enough mass to ignite hydrogen fusion. A planet orbiting a pair of brown dwarfs is already exceptionally rare. Before this, only one other similar system was known. And then, this planet chooses a polar orbit. It does not move in the same plane as the central pair, but sweeps over them at a right angle, tilted 90 degrees relative to their orbital plane. This is the first polar orbit ever discovered in a circumbinary system. Under normal expectations, a planet should form within the plane of the protoplanetary disk itself, because the material in that disk settles into a flat structure under angular momentum. For a planet to end up in a polar orbit, something violent must have happened. Gravitational interactions with other planets, a protoplanetary disk that was already tilted, or some other disturbance during the system's assembly. No one knows for certain yet. But the fact that astronomers had previously seen protoplanetary disks with polar alignments, and now have found a fully formed planet in that same kind of structure, shows that such systems can not only form, but can remain stable long enough to endure. WASP 107b opens up a different kind of anomaly, one rooted not in orbit, but in atmosphere. Most exoplanet atmospheres, when observed from different angles, tend to appear relatively uniform. On tidally locked planets, of course, there are differences between the day side and night side, but viewing them from one direction or another does not usually reveal dramatic changes in atmospheric structure. WASP 107b does not follow that logic. The eastern and western limbs of its atmosphere are clearly different, an east-west asymmetry for which we have no comparable example anywhere in the solar system. That implies that within that gaseous envelope, far more complex dynamics are unfolding than our current models can fully describe. There may be planet-wide storm systems of enormous scale. Its atmospheric circulation may operate in ways more intricate than anything we have predicted. The planet itself is already an anomaly. It is about the size of Jupiter, but with only a small fraction of Jupiter's mass, causing its density to plunge to an extreme low and its gravity to become unusually weak. That low gravity allows the atmosphere to balloon outward dramatically, making it one of the most extremely inflated atmospheres ever known among planets of its mass class. We have no reference point for it anywhere in the solar system. There is no close analog. There is nowhere on Earth where we can recreate such conditions and test the theory directly. In that sense, WASP 107b is not merely a strange planet. It is a natural laboratory, a place where physics is operating in regimes that humanity is only just beginning to learn how to observe. Perhaps one of the ideas that most deeply changes how we think about planets has less to do with how they form than with how completely they can shed one identity and take on another. GJ 1132b seems to have undergone such a journey. Early observations suggested that it was once a mini Neptune, a world with a thick hydrogen-helium envelope wrapped around a rocky core. Then radiation from its host star gradually stripped away that primordial covering. By the usual line of reasoning, the story should have ended there. A bare, rocky planet, slightly larger than Earth, dry and all but finished. But current observations suggest that it still has an atmosphere, just not the original one. The possibility now being considered is that the planet's interior remained geologically active, and that volcanoes continuously released gases that slowly built up into an entirely new secondary atmosphere. Earth itself once followed that path, when volcanic activity released water vapor, carbon dioxide, nitrogen, and many other gases to build the first version of its sky. What humanity had never really considered is that a planet whose atmosphere had been completely stripped away by stellar radiation might grow a new one. If GJ 1132b truly works this way, then atmospheric evolution is no longer a one-way road ending in loss. A planet that has been laid bare may enter an entirely different atmospheric regime, and with that, the very concept of habitability becomes far more flexible. Then there are worlds that challenge us not through their atmospheres, but through the very paths they carve through space. HR 5183b is such a planet. It is 3 times the mass of Jupiter and takes 74 years to complete one orbit around its star. Yet even those numbers are not the strangest part. What truly shatters expectation is the shape of its orbit. For most of its time, this planet lingers almost silently in the outer reaches of its system, then suddenly plunges inward at great speed before being flung back out again. Its orbit is so stretched that it is almost a straight line bent only at the very end. That means extreme environmental swings. In the distant reaches, it is locked in deep cold. When it sweeps close to its star, temperatures surge. Any atmosphere it has, any moons that might exist around it, would have to endure seasons unlike anything in the solar system. One explanation is that there were once at least 2 giant planets in this system that interacted gravitationally. One may have been hurled out into interstellar space, while HR 5183b remained behind, carrying the scar of that encounter in the form of its abnormal orbit. Orbits like this may have been more common in the early stages of planetary systems. Jupiter and Saturn themselves may once have been more eccentric, before gradually settling down over billions of years. It may be that HR 5183b is still too young for that process to be complete. Or perhaps the particular architecture of its system allows such an orbit to persist for a very long time. But if HR 5183b is already extreme, then TOI 241249530b pushes the very concept of eccentricity even further. Its orbital eccentricity is 0.94. A circular orbit has an eccentricity of 0, while a path that is nearly a straight line approaches 1. That means 0.94 is almost a straight line with just enough curvature left to still be called an orbit. This planet dives in so close to its star that the distance far exceeds the kind of extreme we are used to measuring against Mercury, then drifts back out to something like Earth's orbit. The difference in radiation it receives between those 2 ends of its orbit must be violent. And that is still not all. It also moves in the opposite direction of its star's rotation. In the solar system, nearly every planet travels in the same direction as the sun's spin, because all of them were born from the same rotating disk of matter. A retrograde orbit is almost a sign of violence, suggesting that this system must once have been disturbed by powerful gravitational interactions. The tidal forces during each close pass by the star are gradually draining energy from that orbit. Over time, the path will become more circular. The planet will be pulled inward, become tidally locked, and eventually turn into the kind of ultra-hot Jupiter we have already seen in many other systems. What makes this case memorable is that we may be witnessing that phase transition while it is still happening. A planet, in the most literal sense, changing its class before our eyes. And then there is PSJ 2322 to 2650b, a world that seems to gather every absurdity into a single body. It is roughly Jupiter mass and orbits a neutron star like other pulsar planets. But from there, everything immediately veers into something far stranger. Its atmosphere is not dominated by hydrogen, but by helium and carbon. The entire planet is covered in clouds as dark as soot. Under the crushing pressures deep inside, carbon may be compressed into diamond at the core. Tidal forces from the neutron star's immense gravitational field do not allow it to keep a smooth, spherical shape, but instead stretch it into something like a lemon. It completes a full orbit in less than 8 hours, even faster than Earth takes to spin through a single day. That alone is enough to imply an environment of enormous orbital speed and almost merciless tidal stress. No current theory truly explains how a planet like this could have formed. Perhaps it formed farther out and migrated inward. Perhaps it was once a gas giant whose outer layers were stripped away by the neutron star's radiation, leaving only a bizarre remnant behind. Or perhaps it formed from supernova debris like other pulsar planets, but with an entirely different chemical makeup. Scientists have not hidden their confusion over this discovery, and even the paper announcing it could not offer a truly convincing formation model. It feels as if this planet does not merely break the old rules, but shatters even the limits of how far we once thought the rules could be broken. And somewhere within that same picture, the story circles back to the two opposite extremes of light. LTT 9779b, where starlight is thrown back almost like a mirror, and TRES 2b, where light nearly disappears altogether. Between them, and between all the worlds we have passed through, what becomes clearer and clearer is that the universe has no special affection for the familiar. It simply keeps expanding the range of what a planet can be. If there is one planet that makes me feel that physics sometimes knows how to lock itself into a perfect feedback loop, it is LTT 9779b. This world reflects as much as 80% of the starlight that falls on it, brighter than fresh snow and even more reflective than polished silver. It is almost a mirror hanging in the universe. The irony is that the planet itself is only about the size of Neptune and orbits extremely close to its host star, so close that by every familiar expectation, its atmosphere should have been stripped away by stellar winds millions of years ago, and yet that atmosphere remains intact. The answer seems to lie in the metallic clouds high above it, silicates mixed with titanates, not water vapor but compounds more like vaporized glass and titanium. They reflect so strongly that they turn the planet's sky into a mirror, and because they are so heavy, they are not easily blown away by stellar winds the way ordinary gaseous clouds would be. Here, the very thing that makes the planet shine is also what keeps it alive. Its high reflectivity prevents the planet from heating up enough to completely destroy those metallic compounds. As a result, the metal clouds continue to survive, and those same metal clouds, in turn, preserve that reflectivity. A self-reinforcing system so neatly closed that it feels almost unbelievable, and it is precisely that fragile balance that has allowed the brightest planet ever known to survive in a place where it should not survive at all. GJ 1132b takes a different path, a story not of reflection, but of return. This is a rocky world orbiting a red dwarf, and it likely began life as a mini Neptune, with a thick hydrogen-helium envelope surrounding its solid core. Then, radiation from its host star stripped away that primordial atmosphere, leaving behind a naked planet. The story should have ended there, but instead, the planet seems to have built itself a new sky. Volcanic activity from within releases gases outward, creating a second atmosphere with a composition entirely different from the first: hydrogen sulfide, methane, and hydrogen cyanide. The first atmosphere was a legacy of formation. The second comes from geology. That transformation suggests a kind of atmospheric evolution we had never truly witnessed before. It shows that a planet does not necessarily get only one chance. A world can lose its atmosphere, then enter an entirely different atmospheric state later in its life. That unsettles even the way we imagine habitability. A planet that looks dead today may not be finished after all, and a planet that still has an atmosphere now may not keep the same face forever. WASP 107b continues to remind us just how much more complicated planetary atmospheres can be than our elegant models would like them to be. It is about the size of Jupiter, but only around 1/10 of Jupiter's mass, making it one of the least dense planets ever known outside the superpuff class. And then recent observations revealed another surprise. Its atmosphere is not symmetrical between east and west. One side behaves very differently from the other. That does not fit what standard models usually expect for a tidally locked planet. We still expect a strong contrast between day and night. We still predict equatorial superrotation, but we generally assume some degree of symmetry between the eastern and western limbs. WASP 107b does not comply. At its two atmospheric edges, the temperatures are different, the chemical compositions are different, and even the cloud structures are different. That may be the result of an unusual magnetic field. It may be a form of atmospheric instability we do not yet fully understand. Or perhaps its extremely low density creates a kind of dynamics that denser planets never experience. The irony is that this extreme puffiness is both an opportunity and a threat. Its weak gravity allows the atmosphere to spread far from the surface, letting our instruments peer into layers that would be almost unreachable on denser worlds. But that same weakness also means its atmosphere is measurably escaping into space. WASP 107b is in the most literal physical sense, evaporating. TOI 6894b pulls the story back to an even more fundamental question. How do planets actually form? It orbits a red dwarf, the smallest and coolest class of stars, with only about 20% of the Sun's mass. Stars like that usually have protoplanetary disks with much less material. And yet the accompanying planet is nearly Jupiter-sized and has a mass of about 13 Earth masses. Under the Standard Model, that combination is almost impossible. In the usual core accretion picture, the amount of gas and dust around such a small star is simply not enough to build a giant planet. Another theoretical escape route is gravitational instability, in which part of the disk collapses directly into a planet without the step-by-step construction of a core. But even that scenario requires the disk to be sufficiently massive and sufficiently cool, conditions that disks around red dwarfs usually do not have. So when TOI 6894b appears, together with similar planets like LHS 3154b, the problem is no longer a single exception. Either we have underestimated the true masses of protoplanetary disks around small stars, or gravitational instability can happen under conditions we once considered impossible, or there is still some other formation mechanism we have not yet accounted for at all. These planets that should not exist keep appearing, and each new discovery narrows the room for easy explanations just a little more. The only thing that seems certain right now is that the mystery has not yet fully opened. And then, at the end of this stretch of the story, we arrive at Kepler 5.1, a system with 3 super-puff planets at once, as though the universe decided to push the very idea of cotton candy to its absolute limit. Kepler 5.1 is the kind of planetary system that makes you stop for a long time just to accept that the numbers you are reading are not wrong. All 3 planets in this system have densities below 0.1 gram per cubic centimeter, set beside Jupiter at about 1.33, or Saturn at about 0.69. The sheer absurdity of them comes into focus. These worlds are roughly 10 times less dense than Saturn, while their sizes are close to Jupiter's, and their masses only a few times greater than Earth's. If there were any way to stand on their surfaces, the sensation of gravity would probably feel strangely unreal. Their entire structures seem swollen by enormous layers of hydrogen and helium. At first, even the scientists themselves suspected it was just a measurement error. They checked again, then checked once more, but the numbers did not change. Those planets really are that impossibly light. What makes this system so haunting is not only the extreme puffiness, but the fact that all 3 planets are puffed up in the same way. Perhaps they are still young and are continuing to contract after formation. Perhaps some internal heat source is keeping their atmospheres hot and expanded. Or perhaps this is only a short transitional phase, before their atmospheres gradually erode and the planets shrink into something more ordinary. Current observations show that hydrogen and helium really are escaping into space, which means their present appearance may not last forever. In just a few million years, these worlds may look completely different. But this is where the problem becomes unsettling. If this is only a brief phase, then what are the odds that all 3 planets in the same system would be caught in exactly that phase at the same time? That forces people to think in another direction. Either superpuffs are more common than we once believed, or the cotton candy phase lasts longer than the models predicted. And deeper than that lies a question about origin. How did 3 planets in the same system all develop into the same extreme state at once? WASP 12b stands at the opposite end of planetary fate. If Kepler 5.1 feels fragile because it is too light, then WASP 12b feels fragile because it is truly dying. It may have only about 3 million years left. To humans, that sounds enormous. But on cosmic timescales, it is almost negligible, shorter than 5% of the time since the dinosaurs went extinct. This ultra-hot Jupiter orbits so close to its star that tidal forces are pulling it into an egg shape. Its outer atmosphere is no longer fully bound, but is instead streaming toward the star in a continuous flow of matter. With every orbit, it edges a little closer. Each time, the tidal forces intensify, and the rate of atmospheric loss grows greater. At some point, it will reach the Roche limit, where the star's pull fully overwhelms the planet's ability to hold itself together. When that happens, it will be torn apart completely. What makes the sight even more violent is that the planet itself is being heated to over 2,500 degrees Celsius, hot enough for iron, aluminum, and titanium all to vaporize. Its atmosphere therefore glows in visible light, not by reflection, but from its own heat. Observations suggest that about 600 million tons of material are leaving the planet every second and being absorbed by the star. This is no longer a metaphor. The star is literally eating its planet. Many hot Jupiters will probably end in the same way, differing only in whether it takes millions or billions of years. WASP 12b is simply one case we have caught at the final stage, a rare last chapter because that phase passes relatively quickly on the timescale of the universe. 2M1510AB B tells a different story, not of death, but of a balance that feels almost impossible. Just describing this system briefly already piles together three unusual things at once. First, the two central objects are brown dwarfs, failed stars, heavier than planets, but not massive enough to sustain hydrogen fusion. They shine only from leftover heat, not with the true radiance of ordinary stars. Binary brown dwarf pairs are themselves rare. Only about 50 such pairs are currently known. Then this planet orbits both of them at once, making it a circumbinary planet, a kind of orbit already uncommon because it must constantly balance the gravitational fields of two objects. And finally, the real twist is that its orbit is polar. The two brown dwarfs move in one plane, while the planet follows an orbit perpendicular to that plane, sweeping above them both as if refusing every normal arrangement. In theory, a system like this had been predicted. Protoplanetary disks can become tilted or warped, and if a disk forms perpendicular to the orbital plane of a binary system, then planets born within it will naturally follow polar orbits. But 2M1510ABB is the first confirmed case. It turns a theoretical possibility into a real system that actually exists. What makes it so compelling lies in the orbital mechanics themselves. As the two brown dwarfs revolve around each other, the combined gravitational force felt by the planet is constantly changing. At times they both pull in one direction, at others their pulls partly oppose each other. And yet the planet's orbit remains stable, neither flung away nor pulled into one of the central bodies. That tells us there must have been some migratory path that brought the planet from its original configuration into its present state. A polar orbit is not something one expects right at the starting point. It has to be created through evolution, and for that reason, this system becomes an important clue in the broader story of how planetary systems are restructured over time. And then there are worlds that do not even have a star to orbit. Rogue planets may outnumber the stars in the galaxy. They drift through interstellar space as free objects, unbound to any solar system at all. In the Orion Nebula, recent observations have found hundreds of Jupiter-sized objects floating like this. They do not orbit stars. They do not have years in any familiar sense. They simply follow their own paths through the galaxy. And even then, about 80 of them seem to exist in pairs. Two Jupiter-mass worlds orbiting each other while drifting together through the dark, called Jumbo's Jupiter-mass binary objects. Their binary nature makes everything even harder to understand. If they originally formed around stars and were thrown out by gravitational interactions, then how could two planets be ejected together while still remaining bound to one another? That would require conditions almost too special to believe. But if they form directly from the collapse of a cloud of material like stars do, then we have to explain why so many such pairs appear to exist. Every explanation opens yet another layer of mystery. At this point, the feeling of familiarity begins to disappear entirely. Planets are no longer just spheres circling stars in neat orbits. They can swell like cotton candy, be slowly devoured by their parent stars, circle two brown dwarfs at right angles, or wander in pairs through ownerless space. And the farther we go down that list, the harder it becomes to keep believing that what we once called normal ever really meant much at all in a universe like this. There are planets so dark that they are almost impossible to see, not because they do not exist, but because they move through the universe belonging to no star at all. Rogue planets are worlds like these. They emit very little light, and they do not pass in front of a star's disk to reveal themselves, so humanity can usually catch them only through gravitational microlensing or by direct imaging in star-forming regions, when they still retain some leftover warmth from birth. Because of that, the picture we have is almost certainly missing many pieces. Hundreds of cases have already been found, but the true number in the Milky Way may reach into the billions. Some estimates even push it hundreds, perhaps even thousands of times higher than the number of stars. If that is true, then much of the galaxy may be filled with worlds drifting silently between suns, with no sunrise, no sunset, only the faint glow of distant stars and an endless stretch of darkness. To imagine a nearby rogue planet is to imagine a world living without a sun. No light warms its surface, no star shines on its clouds. The only thing keeping it from freezing into total death is the leftover heat from its formation and the energy produced by radioactive decay deep within its interior. Its core may still be molten, convection may still stir inside it. An atmosphere, if it still exists, may continue to circulate even without energy from a star. But above all that, the surface would be a realm of absolute freezing. Water, if present, would become ice layers kilometers thick. Methane would solidify. Nitrogen would condense. The atmosphere would be thin and cold. And yet, beneath that ice, there could still be subsurface oceans warmed by internal geothermal heat, a possibility reminiscent of Europa, but without needing tidal heating from a parent planet. No one yet knows whether life could find a way into places like that. But the sheer possibility that rogue planets may exist in such enormous numbers is already enough to make them an environment we cannot afford to ignore. Then, at the complete opposite extreme, there are planets that do not lack a star, but have almost too much star. Kelt, 9b, is nearly the outer limit of the heat a planet can endure. It is an ultra-hot Jupiter, orbiting so close to its host star that its dayside temperature reaches around 4,300 degrees Celsius, hotter than many stars. There, hydrogen can no longer remain peacefully in molecular form. It is torn apart into individual atoms. The dayside atmosphere is therefore more atomic than molecular. When that gas flows to the planet's night side, the temperature falls enough for the atoms to recombine into molecules, only to be broken apart again when circulation brings them back to the bright side. Spitzer detected that very cycle of constant dissociation and recombination. A year on Kelt, 9b lasts only 36 hours. It is tidally locked, with one face permanently turned toward the star. The brutal thermal contrast between the two hemispheres creates supersonic winds that redistribute some of the heat, though not enough to save the dayside from temperatures high enough to vaporize metals. In this planet's atmosphere, iron and titanium exist as individual atoms. Magnesium and calcium do too. Even some light rare earth elements have been identified. It orbits an A-type star, bright, hot, and massive, the kind of star that lives fast and dies fast. One day, when that star swells outward, it will swallow the planet whole. But even before that moment, Kelt, 9b may already have begun to lose its atmosphere, with stellar radiation driving particle after particle out into space. Over time, it may be stripped bare, leaving only a glowing rocky or metallic core, or vanish entirely. TIC 241249530b shows another path toward planetary extremity. Its orbit does not resemble a planet's so much as a comet's. Its eccentricity reaches 0, 94, making its path almost a straight line, with just enough curvature left to remain within the definition of an orbit. At its closest point, it dives toward its star far more closely than Mercury ever approaches the Sunday. At its farthest, it drifts out to something like Earth's orbital distance. Along with that swing comes an almost unimaginable variation in temperature, scorching when close in, then dropping sharply as it retreats. Its seasons do not come from axial tilt, but from the abnormal shape of the orbit itself. And then there is one more detail that makes the picture even more violent. This planet moves in the opposite direction of its star's rotation. In most planetary systems, prograde motion is the natural signature of formation from a single rotating disk of matter. A retrograde orbit almost always suggests a violent past, perhaps strong gravitational interactions with another planet, perhaps the disturbance of a passing star. The tidal forces acting now are gradually circularizing that orbit. Over millions of years, the planet will spiral inward, settle into a circular path, and likely become a true hot Jupiter. What makes TIC 241249530b so special is that we are catching it in the middle of that journey, like a frame from a film taken at the exact moment a planet is changing its fate. WASP 12b is no longer in the middle of the journey. It is already too close to its star, too deep into the final phase. Just 26 hours is enough for it to complete one orbit around a yellow dwarf similar to the Sunday. That distance is so small that closeness itself has become a death sentence. The star's gravity pulls the planet into a distorted shape, swelling toward the star and stretching out on the far side. Tidal forces are tearing it apart piece by piece. At the same time, intense radiation heats the upper atmosphere so severely that matter begins to escape, and some of that material may even form a disk around the star. WASP 12b is evaporating, eroding, being devoured. Current models give it about 3 million years more. That sounds long, but on astronomical timescales it is almost nothing, only a brief delay before disappearance. In the end, there may be nothing left, or perhaps only a small, dense, overheated rocky core, the corpse of a planet orbiting the star that killed it. WASP 121b carries many shades of the same tragedy. This too is a tidally locked, ultra-hot Jupiter, with a dayside temperature above 2,700 degrees Celsius. At that level, iron, aluminum, and titanium no longer remain quietly locked inside rock or mineral clouds, but exist as gases in the upper atmosphere. The temperature contrast between the dayside and nightside drives winds above 16,000 kilometers per hour, so fast that storms on Earth are almost meaningless as a comparison. The planet circles its star in about 30 hours, close enough that it too is being stretched, bulging toward the star under tidal forces. It is no longer a round world in any familiar sense, but an object being deformed by its overly intimate relationship with the source of light that sustains it. From rogue planets frozen in interstellar darkness to ultra-hot Jupiters being burned alive beside their stars, the range of conditions the universe permits for a planet is far wider than any intuition we once built for ourselves. There are worlds with no sun at all. There are worlds slowly being killed by their own sun. And between those two extremes, planets are not merely places that exist. They are also processes in motion, objects that can always change state, change orbit, change atmosphere, and even change their own fate. On worlds like WASP 121b, the heat does not come only from the star blazing in front of them. The planet's own distorted shape under tidal forces is also generating extra heat from within, as though its entire body were being kneaded over and over until it began to glow. So when stellar radiation and tidal heating pile on top of one another, WASP 121b is pushed into the ranks of the hottest planets ever known. Its atmospheric spectrum has been studied in great detail, and water vapor has been found there. But here, water vapor suggests nothing gentle. It is vapor existing at temperatures high enough to make steel boil away. The truly strange chemistry of this planet lies elsewhere. Titanium oxide and vanadium oxide also appear in the atmosphere. Compounds like that should not be stable under such brutal conditions, and yet they are there. It feels as though the planet must be constantly pumping them up from deeper inside. Perhaps temperatures in the lower atmosphere have risen so high that rock itself begins to evaporate, and material from the mantle is gradually drawn upward, creating a kind of chemistry utterly alien to any colder environment. Then if we step away from that extreme heat and look toward the opposite side of light, LTT 9779b appears as another paradox. It reflects as much as 80% of the starlight that reaches it, surpassing even Venus and becoming the most reflective planet ever discovered. Earth reflects only about 30%. Venus, with its dense sulfuric acid clouds, reaches about 75%, but LTT 9779b goes even beyond that. This is a Neptune-sized world orbiting extremely close to its star, with a year shorter than a single day on Earth. By familiar logic, it ought to be a hot Neptune that has already lost its atmosphere and been stripped down to its core. And yet it has managed to keep its gaseous envelope. The secret seems to lie in metallic clouds, silicates and titanates, materials like glass and titanium salts, condensing into reflective droplets spread across the planet. They do not merely bounce back most of the incoming radiation, keeping the atmosphere from heating so much that it can no longer maintain its present structure. They are also heavy enough not to be swept away by stellar winds like ordinary clouds of gas. Here, the very thing that makes the planet shine is also what helps it survive. And because of that, LTT 9779b forces people to rethink things. Perhaps atmospheres rich in metallic clouds are not as rare as we imagined, and most hot Neptunes were simply stripped bare before we had the chance to recognize them. Or perhaps, as so often happens in exoplanet science, it is our model that needs to change. That had already happened very early on, with the first exoplanets themselves. PSRB 1257 plus 12 has not one but 3 planets, yet they do not orbit a normal star. At the center of the system is a pulsar, the remnant of a supernova, where the stellar core has been crushed into a neutron star, so incredibly small, yet so unimaginably dense, that a teaspoon of its material would weigh billions of tons on Earth. A pulsar spins extraordinarily fast, hundreds of times per second, sweeping radio beams through space like a lighthouse. PSRB 1257 plus 12 completes one rotation in just 6.2 milliseconds. That almost perfect regularity turns it into a cosmic clock. When planets orbit it, their gravity causes the pulsar to wobble ever so slightly, and that wobble is enough to alter the arrival times of its radio pulses at Earth. From those minute variations, 3 planets were discovered in 1992, becoming the first confirmed exoplanets ever found. The innermost planet has a mass less than twice that of Earth, among the lowest mass exoplanets ever known. The other 2 are larger, each weighing a few Earth masses. It is very unlikely that they survived the explosion that created the pulsar. Much more likely is that they formed afterward, out of a disk of leftover material around the neutron star. Second-generation planets, born after the death of a star. They exist in an environment flooded with X-rays, gamma rays, and charged particles, where any atmosphere would be hard-pressed to survive for long, and the surface, if there is one, is likely nothing but rock sterilized by radiation. And yet, despite all of that, they are still there, orbiting a stellar corpse in the dark. TOI 6894b challenges astronomy in a completely different way. It does not orbit a pulsar, but a red dwarf only about 20% the size of the Sunday. The problem is that the planet itself is nearly the size of Jupiter. Under the core accretion model, that should be almost impossible. To build a giant gas planet, a protoplanetary disk needs a great deal of material, whereas small stars usually come with smaller, poorer disks. And yet TOI 6894b still exists, with a mass around half that of Jupiter and an inflated state caused by heating from its host star. This discovery, announced in 2025, immediately forced astronomers to go back and re-examine the foundations of their theory. Perhaps the core accretion model needs much deeper revision. Perhaps small stars can still host larger disks than we once believed. Whatever the final explanation turns out to be, The mere fact that this planet exists is already enough to repeat the most familiar lesson in exoplanet science. Every time we think we understand the rules, the universe quietly presents an exception large enough to shake the entire old framework. Perhaps the answer to planets like TOI 6894b does not lie in patching the old model, but in accepting an entirely different pathway of formation. Instead of growing gradually through core accretion, perhaps part of the protoplanetary disk collapsed directly into a planet once the mass became large enough. That is the gravitational instability scenario. The problem is that this mechanism usually requires very special conditions that, until now, people did not think could exist around red dwarfs. And then LHS 3154b appears, as if to emphasize that TOI 6894b is not alone. This is another world far too large for its star, 13 times Earth's mass, yet orbiting a star much smaller than the Sunday. That ratio leaves even our best current models struggling. Later studies may eventually show how such worlds formed. Or it may be that the deeper we dig, the larger the mystery becomes. But if planets like these continue to be found around low-mass stars, then the issue will no longer be a handful of scattered exceptions. Either the theory of planet formation will need to change drastically, or we will have to accept that nature sometimes produces rare exceptions on a scale that is almost impossible to predict. Either way, every impossible planet keeps quietly expanding the boundary of what we think is possible. 2M1510ABB does not merely drift away from the model. It almost seems to step into a different plane of strangeness altogether. It orbits two central objects at once, which in itself is not entirely unprecedented. But those two objects are brown dwarfs, failed stars that never became massive enough to ignite hydrogen fusion. Before this, only one other circumbinary planet was known around a brown dwarf pair, so the setting alone is already rare enough. But what truly made astronomers stop in their tracks was the orbit. Most planets move almost in the same plane as their stars, like a flat spinning record. Our own solar system is like that too, because everything formed out of a flat protoplanetary disk of gas and dust. But 2M1510ABB refuses to follow that rule. It orbits perpendicular to the plane of the brown dwarf pair, as though the two central bodies are spinning sideways while the planet loops above and below them like a vertical carousel. That is a polar orbit, and this is the first planet ever confirmed in such a state in a binary system. It almost certainly was not born in that orientation. Something must have forced it far out of the original plane. Perhaps a gravitational interaction with another body. Perhaps a close passage by a wandering star. Whatever the cause, this discovery shows that planetary migration does not happen only inward or outward with respect to the host star. Sometimes, the orbital plane itself can be bent. WASP 107b tells a different story, one in which the strangeness lies in the atmosphere. It is about the size of Jupiter but only 1/10 of Jupiter's mass. A true superpuff, weak gravity, low density, an atmosphere blown outward to an extreme degree. All of that makes it an almost ideal target for spectroscopic observation, because light passes through more layers of gas and leaves clearer fingerprints behind. But then, in 2023, something unusual appeared. Its atmosphere is not symmetrical. The eastern and western limbs are different, in both temperature and composition. On a tidally locked world, where one face always points toward the star and the other remains in darkness, people expect a day-night contrast, but they still assume the eastern and western sides will remain relatively symmetric. WASP 107b does not follow that expectation. Its atmosphere suggests a far more complex dynamical system, perhaps extremely powerful jet streams, unusual wind patterns, or local weather systems unlike anything we have seen elsewhere. The solar system offers us no comparison, and because of that, almost every measurement of this planet becomes a new surprise. GJ 1132b, meanwhile, is a story of transformation. It orbits a red dwarf, is slightly larger than Earth, and is a rocky world rather than a gas planet. For a long time, people thought it was simply a tidally locked planet, perhaps barren and not especially remarkable. But then its atmosphere appeared, and that atmosphere seemed rich in hydrogen, something more commonly associated with gas giants or mini-Neptunes than with rocky planets. The proposed explanation makes the whole story much deeper. Perhaps GJ 1132b really was once a mini-Neptune, wrapped in a thick gaseous envelope. But its host star is an active red dwarf, prone to violent flares and harsh radiation. The original atmosphere was stripped away into space. What remained was the rocky core beneath, and that rocky core was still geologically alive. Over millions of years, volcanic activity and outgassing released carbon dioxide, hydrogen sulfide, and many other substances. From the planet's own interior, a second atmosphere began to form. This is the first evidence that a world may be able to regrow an atmosphere after losing its first one. A planet, in that sense, does not get only one chance. If this can happen on GJ 1132b, then other rocky worlds around active stars may go through the same kind of life cycle. HR 5183b suggests yet another kind of chaos, so much so that it has been nicknamed a wrecking ball. This is a super Jupiter 3 times the mass of Jupiter, taking 74 years to complete a single orbit. But what makes it stand out is not that timescale, but the shape of the orbit itself. Its eccentricity of about 0.9 stretches the path to an extreme degree, almost to the boundary where a slightly greater push might let it escape the system entirely. For most of its time, this planet lingers in the cold outer reaches, then it suddenly dives toward the star like a giant comet before being hurled back outward again. At its closest point, it approaches something like Mercury's distance. At its farthest, it extends beyond the equivalent of Jupiter's orbit. That range is enough to cause serious disruption to anything else in the system. If there were ever other planets there, HR 5183b may well have disturbed their orbits, perhaps even flung them away long ago. It may be the reason this system now appears so empty. That abnormal orbit is most likely the scar left by violent gravitational interactions in the past, perhaps with another planet, perhaps with a passing star. It was discovered through the radial velocity method, a kind of detection that demands patience almost on the scale of classical astronomy itself. You have to track the wobble of the star for many years, even decades, before an orbit this long can reveal itself. And that may be the clearest thing HR 5183b reminds us of. Planetary systems are not static diagrams. They are structures in constant change, always colliding, always being rearranged by the force of their own gravity. The more I look at planetary systems, the more I feel that stability is only a temporary appearance. Planets can migrate, orbits can change. A system that looks orderly today may once have passed through phases of chaos so violent that nothing remained in its original place. WASP 12b is a clear example of the dark side of that process. It circles its star in only about 26 hours, so close that the star's gravity is literally pulling it out of shape into something like an egg. Its atmosphere is being stripped away, matter is being drawn from the planet into a spiral flow toward the star, and the ending is almost already written. In about 3 million years, that world may disappear completely. It is tidally locked, with one face always turned toward the star, and that face is even hotter than the already extreme 4,000 degrees Fahrenheit threshold, hot enough for metals to vaporize. In that dying atmosphere, titanium oxide and vanadium oxide are still present, and when they move to the night side, they condense into clouds of metallic oxides. But the most haunting detail is still the rate of mass loss, about 100 billion tons per year. For a giant gas planet, that destruction does not happen in an instant, but it is already a one-way road. WASP 12b shows the final endpoint of planets that have migrated too close to their stars, where tidal forces cease to be merely a shaping influence and become a death sentence. And precisely because it is dying, it becomes especially useful to science. As its outer layers are peeled away, what lies beneath begins to emerge, like a geological excavation on a planetary scale. Gas giants usually hide their deeper structure, but here, the process of destruction is accidentally giving us a chance to observe the composition of lower layers. WASP 1-2b therefore does not only tell the story of a world being devoured, but also helps explain how planets migrate, what mechanisms bring them close to their stars, and what boundary separates a hot Jupiter that can remain stable for billions of years from a planet that has gone too far and has no way back. At the complete opposite end of light is LTT 9779b. If there are worlds that absorb nearly every photon that hits them, this planet does the reverse. It reflects up to 80% of the light it receives, the highest albedo ever recorded for an exoplanet. It is like a giant mirror hanging in the dark. The strange thing is that this world orbits its star in only about 19 hours, sitting right in the hot Neptune desert, where Neptune-sized planets close to stars are so rare they nearly disappear from the statistics, because stellar radiation should have blown their atmospheres away long ago. And yet LTT 9779b survives. Its atmosphere contains metallic clouds, especially titanate clouds, reflective enough to send most of the starlight back into space. Those same heavy materials are also likely too dense to be easily swept away by stellar winds, turning the metallic clouds themselves into a kind of shield. The planet is still extremely hot, around 3000 degrees Fahrenheit, but the atmospheric pressure is high enough for metals to condense into clouds instead of existing only as vapor. There, reflection is not merely an appearance, it is a defense mechanism. LTT 9779b therefore shows that in environments that seem impossible, an atmosphere can still survive if chemistry and physics happen to align in exactly the right way. Then comes PSR J23222650b, a world newly announced in 2025, and one that almost immediately became a problem. It orbits a pulsar, like the PSR B 1257+12 system, but this time it is a planet roughly the mass of Jupiter. At the center of the system is a neutron star only about 20 kilometers across, so small it is almost hard to believe. Yet its gravitational field is strong enough to distort the planet into something like a lemon, stretched in the direction facing the pulsar. The planet completes one orbit in less than 8 hours. Its atmosphere also does not resemble that of a familiar gas giant, but is dominated more by helium and carbon than by hydrogen, and is covered in dark soot-like layers. Deep inside, carbon may be compressed into diamond. The mere existence of such a planet is already enough to leave current theories struggling. A pulsar is born from a supernova, and a supernova should have destroyed any nearby worlds. Perhaps this is a second-generation planet, formed from debris after the explosion, but that idea still does not fully explain the unusual atmospheric composition and extremely short orbit. It may also be a captured rogue planet, though that possibility seems very unlikely. And when the usual explanations all fail to feel adequate, people begin to consider a more unsettling possibility. Perhaps this is a type of object sitting at a boundary that our current classification system is not even wide enough to contain. At this point, what emerges is no longer a scattering of isolated exceptions, but a clear pattern. We have seen planets darker than coal, bright as mirrors, worlds with glass rain, worlds with iron rain, worlds made of crystallized carbon, planets with no parent star, planets orbiting dead stars, worlds in polar orbits, atmospheres that are asymmetric, atmospheres that are stripped away and then regrown, and even planets being torn apart by the very stars they orbit. And while that list is already enough to make every old concept feel too narrow, it is still only a very thin slice of the whole picture. Out of the billions of planets in the Milky Way, humanity knows only a few thousand. The strange worlds tend to reveal themselves first, either because they stand out or because our search methods are biased toward detecting exactly that kind of anomaly. That almost certainly means that out there are countless more planets with conditions for which, right now, we do not even have enough language to imagine them. That is why every new discovery does more than add another name to the list. It forces the entire theory to shift along with it. TOI 6894b is a very clear example. Announced in June 2025, it immediately caused trouble because it orbits a red dwarf only about 20% the size of the Sun, while the planet itself is nearly the size of Jupiter. According to current models, a star that small should not have a protoplanetary disk rich enough in material to create a giant gas planet. But the planet is there, and LHS 3154b is a reminder that TOI 6894b is not alone. The more worlds like these appear, the harder it becomes to treat them as rare accidents. The problem may no longer lie in a few planets being wrong, but in the possibility that what we once thought was right about the formation of planetary systems was too narrow from the very beginning. LHS 3154b is one of those worlds that forces us to look back at the very foundations of theory. Discovered in 2023, it has about 13 times Earth's mass, yet it orbits a star so much smaller than the Sun that the ratio between planet and star becomes almost impossible to accept within familiar models. Researchers have called it impossible, and that feeling is not an exaggeration. Discoveries like this are not just a few stray points falling off the graph. They are more like cracks, revealing that our current understanding of planet formation is still missing some very important pieces. Perhaps small stars can accumulate more material than we once thought. Perhaps under certain conditions, planet formation is simply more efficient. It is also possible that these planets were born farther out, where material was more abundant, and then migrated inward. Or, more deeply still, perhaps we are still overlooking a fundamental principle about how planetary systems are truly assembled. Wherever the final answer lies, planets like TOI 6894b and LHS 3154b are forcing astronomers back to the drawing board, testing scenarios once considered unlikely, and even re-examining mechanisms that had already been set aside. 2M1510ABB, by contrast, does not attack theory through size or mass, but through the geometry of its orbit. This is a circumbinary planet, orbiting two central objects at once. That is already rare, but not yet what makes it feel almost surreal. The central pair here are brown dwarfs, failed stars that never reached the threshold needed to ignite nuclear fusion. Before this, only one other such system had ever been known, but the feature that truly makes people stop is the planet's orbit. It does not lie in the plane where the two brown dwarfs circle one another, but instead stands upright, perpendicular to it. If you imagine the brown dwarf pair spinning horizontally like a wheel, then the planet loops up above and down below them like a vertical ride, crossing the whole system at a perfect 90-degree angle. That is a polar orbit, and this is the first polar circumbinary planet ever discovered. Before this, astronomers had suspected that such structures might exist because they had already seen protoplanetary disks aligned at polar angles. But seeing a fully formed planet living stably in such an orbit is an entirely different matter. Under the standard picture, planets form in a flat disk of material around a young star, and because the disk itself is flat, the orbits should remain in that same plane. A polar orbiting planet suggests that some powerful disturbance once occurred, perhaps another planet, perhaps a passing star, or perhaps the disk itself was tilted from the very beginning. Whatever the cause, 2M1510ABB is opening a door into the story of planetary migration, many-body dynamics, and the way orbits can be rewritten over millions of years. WASP 107b tells the story of an atmosphere that refuses to behave in any predictable way. It is about the size of Jupiter, but only 1/10 as massive, a true superpuff, with an atmosphere inflated to the point of fragility. Precisely because that atmosphere is so extended, more light can pass through it, leaving behind clearer spectroscopic signals. But when astronomers looked closely, what emerged was not a neat atmospheric structure, but a pronounced mismatch between east and west. Different temperatures, different compositions, one side unlike the other. In the solar system, we have no planet close enough to serve as a comparison for that kind of structure. This asymmetry suggests that inside WASP 107b's atmosphere, there may be uneven wind flows, long-lived high-pressure regions, or even local weather systems unlike anything seen anywhere else. In that sense, this planet is not merely an odd exception, but a natural laboratory for studying how energy spreads, how chemistry mixes, and how atmospheres behave when gravity is too weak to keep everything within familiar bounds. GJ 1132b brings a different kind of transformation, one that feels deeper and almost richer in implication. This is a rocky world, slightly larger than Earth, orbiting a red dwarf. For a long time, people thought it was not especially remarkable, except perhaps for being tidally locked and rather barren. But then, an atmosphere appeared, and that alone forced the story to be rewritten from the beginning. Scientists now think it may once have been a mini Neptune, wrapped in a thick hydrogen envelope. Later, intense radiation from its host star stripped away that primordial atmosphere. Under the old reasoning, the planet should have ended there as a bare rocky core, but it did not. From its interior, through volcanic activity and outgassing, substances like carbon dioxide, nitrogen, and possibly other compounds continued to be released. A second atmosphere gradually formed, one no longer inherited from the planet's birth, but produced by geology. If that is correct, then this is the first world to offer clear evidence that a planet can lose its original atmosphere and then create a new one for itself. That makes the whole idea of planetary evolution far more complex. A planet does not simply move from youth to age, from stability to decline. It can change type, change sky, even change the very state of its existence in ways we had not truly imagined before. HR 5183b, meanwhile, is proof of how lasting the scars of gravitational chaos can be. This is a super Jupiter 3 times the mass of Jupiter, and it takes 74 years to complete one orbit. But what makes it stand out is not that long period, but the shape of its orbit, stretched to an extreme, like a ring pulled badly out of shape. For most of its time, this planet stays very far from its star, almost drifting slowly through the outer reaches of the system. Then suddenly it plunges inward, sweeping through the inner regions at tremendous speed before being flung back outward again. At one point it lies beyond something like Earth's orbital distance. At another, it falls closer in than Mercury. That difference implies violent temperature swings, from freezing cold to scorching heat and back again. An orbit like that does not arise naturally. One reasonable explanation is that in the past, there was another giant planet in the system, and the two worlds scattered one another through gravitational interactions. One may have been thrown out into interstellar space, or cast so far away that we have not yet seen it. The survivor, HR 5183b, retains its warped orbit as a relic of that era of chaos. In that sense, it shows not only how violent planetary systems can be, but also reminds us that the calm appearance of today's solar system does not necessarily imply a peaceful past. Planets can migrate, orbits can change. Systems that look stable now may once have passed through phases far more violent than anything we see today. That may be what hangs over the entire story of exoplanets. We once believed we understood fairly well where planets should form, what they should be made of, and what planetary systems ought to look like. We assumed gas giants had to stay far from their stars. We assumed planetary systems would more or less resemble the solar system, with orderly, predictable structures. We assumed an atmosphere was something a planet either had and kept, or lost once and for all. But each discovery keeps bending those assumptions. Planets can orbit pulsars. They can wander without a parent star. They can circle two stars, or two brown dwarfs. They can be pulled into polar orbits. They can have asymmetric atmospheres. They can lose one atmosphere and grow another. They can migrate, deform, change their fate. Each such discovery expands the boundaries of the possible, while also reminding us that what we see is still limited by the methods we use to search. We are best at finding planets that are large, close to their stars, or cross in front of them from a favorable angle, which means that out there, very likely, there are countless other worlds still waiting. Not only strange, but strange in ways we do not yet have the tools to detect and do not yet have the concepts to name. Perhaps the most important point lies not in the planets we have already seen, but in the enormous number of planets that still remain hidden from view. Worlds too far from their stars are almost impossible to detect with current technology. Rocky planets orbiting faint stars can easily sink into the background darkness. Objects on wide orbits may take decades, or even longer, to complete a single revolution, and we simply have not observed long enough to read their patterns clearly. Because of that, the exoplanet picture humanity is holding in its hands is distorted from the very beginning. We see the worlds that are easiest to see, and many of those just happen to be bizarre worlds. That almost certainly means that beyond the fragile bright zone of our current data, there are still countless other planets, perhaps even more extreme, more alien, with atmospheres containing compounds we have never thought to consider, and surfaces whose geology lies beyond the intuition we currently carry with us. In that darkness, James Webb is beginning to pull more light toward us. This telescope does not merely see planets, it reads their atmospheres. It recognizes molecules, names chemicals, measures temperatures across different regions of the same world. Water vapor, carbon dioxide, methane, sulfur compounds, thermal gradients, cloud structures, weather patterns, all of it is gradually emerging from the faint signals carried by light. And then there will be instruments still farther ahead, the extremely large telescope, the Habitable Worlds Observatory. They will see smaller planets, read atmospheres in greater detail, and push the search for biosignatures to a new depth. We cannot touch those worlds. We cannot send probes to them. We cannot set foot on their surfaces. But the strange thing is that every photon that crosses those light years still carries enough information to tell a story. Every spectrum is an inventory of composition. Every transit across a star reveals size and orbit. Every tiny wobble of a star is a signal. The universe is not silent. It is speaking in wavelengths, in oscillations, in the faint dimming of distant suns. And what it is saying, more and more clearly, is that planets do not obey the simplicity we once expected. Rules that once felt fundamental now appear far more flexible. Strange exoplanets no longer seem like a few exceptions falling off the edge of theory, but like constant reminders that the theory itself is still incomplete. For billions of years, the universe has been experimenting with planet formation in more ways than we imagined. The results of those experiments now appear in the darkest worlds, the brightest worlds, the hottest worlds, the puffiest worlds, in planets where it rains glass, where it rains iron, in spheres of crystallized carbon, in worlds orbiting dead stars, in worlds orbiting no star at all, in planets with polar orbits, asymmetric atmospheres, or sizes that current models cannot even contain. Each such discovery forces the definition of planet to stretch a little wider. Perhaps our greatest mistake was simply turning one example into a standard. We grew up on a single planet, in a single system, and from that quietly assumed that Earth was the normal type, that the solar system was the typical structure. But Earth is not the standard. It is only one possibility. The solar system is not the template. It is only one example among countless examples the universe allows. And so, when humanity looks up at the sky and asks whether we are alone, even that question is beginning to change its meaning. Finding life beyond Earth would still be a discovery powerful enough to shake philosophy, religion, science, and our entire sense of humanity's place in the universe. But strange planets are already teaching us something even deeper. If life exists, it may not need to resemble what we are trying to find. For a long time, the search for life has been guided by the image of a second Earth. Liquid water, moderate temperatures, a stable atmosphere, an orbit within the habitable zone. But that is a strategy built from the only denominator we know, Earth itself. What if biology is far more flexible than that? Even on our own planet, there are clues, unsettling in the most beautiful way. Bacteria living in boiling hot springs, microorganisms surviving deep beneath the ocean floor, organisms clinging to life in acid lakes, strains of bacteria enduring radiation levels high enough to kill almost everything else. If a single world like Earth can produce life this resilient in such extreme places, then the planets we call hostile may be more open than we think. Somewhere, perhaps, in the upper atmosphere of a hot Jupiter, there may be forms of life floating between hydrogen and helium clouds. Perhaps super puffs with their enormous atmospheres could host airborne ecosystems we do not yet have the imagination to describe. Tidally locked planets, with eternal day on one side and eternal night on the other, may support forms of life adapted to extreme thermal differences. Even rogue planets drifting through interstellar space may hide subsurface oceans kept liquid by their own internal heat. So each strange planet that is discovered does more than expand the list of places that exist. It expands the map of environments that might support life. They force us to step outside Earth-centric bias and begin thinking about biochemistries based on different solvents, different energy sources, or metabolic systems that still sound like science fiction to us now. JWST is beginning that search by examining exoplanet atmospheres for biosignatures, oxygen, methane, phosphine, or combinations of gases that should not coexist unless some process is constantly replenishing them. But even here, caution is necessary, because that very way of searching still quietly assumes that life beyond Earth will leave behind biological waste signals like the life on Earth does. But what if alien biology produces entirely different byproducts? If the signatures of life are chemicals we have not even thought of yet, then failing to see familiar signs would not necessarily mean that nothing is there. That is why planets like PSRJ 23222650b or TOI 6894b matter far beyond the surface strangeness that first draws attention to them. No one thought a planet could exist around a pulsar after a supernova until one did. No one thought a near Jupiter-sized planet could orbit such a small red dwarf until TOI 6894b appeared. Each world that should not exist forces humanity to revise some part of its theory, and with every such revision, the boundary of the possible moves farther away. And along with it, the list of places where life might take root grows longer. The search for life beyond Earth, then, is no longer just a hunt for a copy of home. It is the process of learning to accept that life may be far more resilient and far more flexible than our intuition suggests. The next generation of telescopes will continue to push that question farther with a level of detail we can currently only imagine. But even before we receive an unmistakable signal of life, strange exoplanets have already taught us a lesson large enough on its own. The universe is not only vast, it is richer, stranger, and more inventive than any framework humanity has ever built in order to make it feel familiar. The deeper we go into the story of exoplanets, the clearest feeling is not that we have learned so much, but that we have only touched the outermost shell. Thousands of exoplanets have been discovered, and that sounds enormous. But set against the hundreds of billions of stars in the Milky Way alone, and the likelihood that most of them host planets, everything we currently possess is only a tiny fragment of the full picture. And yet even within that tiny fragment, the universe has already revealed worlds beyond easy explanation, planets that do not fit the theory, systems that should not have formed, atmospheres that defy prediction. That makes me think the strangest things may not even have appeared before us yet. As telescopes grow more sensitive, as detection methods become more refined, as humanity truly surveys a larger portion of the galaxy, it is very possible that the most bizarre worlds will be those for which we currently do not even have enough language to imagine. There may be planets with magnetic fields so strong they distort atomic structure, surfaces where matter exists in states we have only begun to approach in theory, or atmospheres so dense that the boundary between gas and liquid no longer carries any clear meaning. In truth, the universe has been steadily training us to grow used to being surprised. Before it was discovered, iron rain on WASP 76b would have sounded like delirium. Glass rain on HD 189733b as well. The near-total darkness of TRES 2b, or the absurd lightness of the cotton candy planets, all once stood outside the normal frame of imagination. But then, one by one, those worlds appeared, and with each new discovery, the boundary of what is possible was pushed back a little farther. The discoveries still to come will likely do the same, force us to revise assumptions, rewrite theories, and widen the borders of planetary science. The beauty of it is that strange exoplanets do not speak only about distant places. They also cast light back onto our own solar system. When we look at ultra-hot Jupiters burning beside their stars, Jupiter suddenly appears in a very different role from that of a gentle giant. Its gravity has deflected comets and asteroids, shielding the inner solar system. Without Jupiter, Earth might have suffered many more impacts, and complex life may never have had the chance to evolve. Saturn's rings were once considered almost unique, until we found ring systems around exoplanets. Mars was once the obvious candidate in the search for life, until the subsurface oceans of Europa, Enceladus, and Titan forced us to change our perspective. Every new discovery out there reflects back upon the familiar region of the universe around us, clarifying what is truly special about Earth and what is merely one possibility among countless others. Earth has a habitable zone, liquid water, a magnetic field, a stable climate, and an atmosphere protective enough without being too harsh. That combination may be rare, or it may not. We do not yet know. But the sheer diversity of exoplanets has already made one thing feel almost certain. Earth-like worlds must exist somewhere. The question is no longer whether they exist, but how common they are, and whether any of them actually host life. Then from origins, the question stretches onward to fate. WASP 12b is dying before our eyes, being stretched, stripped, and ultimately destined to vanish in a few million years. Rogue planets tell a different kind of ending, cast out of their systems, drifting through interstellar darkness. Will they remain frozen forever? Or could some of them one day be captured by another star? Could a planet pass through multiple parent stars over the course of its existence? Those questions do not speak only about distant worlds. They speak about the future of our own solar system as well. In about 5 billion years, the Sun will swell into a red giant, swallowing Mercury, Venus, and perhaps Earth. The outer planets may survive, but the system we know will no longer be recognizable. There may be planetary remnants orbiting the white dwarf core of the Sunday. Some worlds may be flung outward and become rogue planets. When we observe planetary systems at different stages of evolution, we are not only looking at them, we are also looking at our own past and future. In that sense, strange exoplanets really are time machines. Young systems show us how planets form, stable systems show us how they endure, and dying systems show us the end. And that story is far from over. New planets are constantly being added to the list. New techniques are still being developed. New telescopes are still being built. Exoplanet science is not standing still. It is accelerating. In the coming decade, humanity will find thousands more worlds and describe hundreds of atmospheres with far greater precision. We may detect biosignatures, we may not, but either outcome would change almost everything. If we find life, we will know that biology is not Earth's exclusive privilege, and that thought alone would be enough to rewrite science, philosophy, religion, and the way humanity understands itself. If we find nothing, that would instead suggest that life may be so rare that Earth is even more special than we once dared to believe, and in that case, our responsibility toward consciousness and life would become far heavier. But even before that answer arrives, strange exoplanets have already taught us the most important lesson. The universe is stranger, more diverse, and more inventive than all the limited experience of our species ever allowed us to believe. The darkest worlds, the brightest worlds, worlds where it rains iron, worlds where it rains glass, planets orbiting dead stars, planets orbiting no star at all, worlds that formed where they should not have formed, worlds that survived what they should not have survived, all of them are real. And these are only the worlds that current technology has happened to be able to reach. Planets large enough, close enough, bright enough, or unusual enough to reveal themselves. Out there are almost certainly worlds stranger still, systems that may yet shatter the last assumptions we continue to hold. Humanity will find them, because we have only just begun this exploration. The tools will grow better, the methods will grow sharper, new generations of astronomers will push farther into the unknown, and the farther we go, the clearer it becomes. Strange exoplanets are not random exceptions. They are the way the universe reveals its true nature, more diverse than any pattern, more creative than any prediction, and always larger than the imagination of the observer. Perhaps that is the deepest lesson of all. Not merely that those specific planets exist, but that the universe refuses to be locked inside our expectations. Nature always finds configurations that theory has not yet prepared for. And if humanity is willing to look long enough and carefully enough, it will keep finding ways to surprise us. Right now, we are standing at the threshold of a galaxy we have only just begun to learn how to read. More than 6,000 confirmed exoplanets sounds like a great triumph, until we remember that out there are hundreds of billions of stars, and most of them probably carry their own worlds. We have sampled only a tiny fraction of the whole picture, and yet even that much has already been enough for the universe to break almost every first assumption we ever built. We once thought planetary systems would resemble the solar system. Neat, predictable, rocky planets close to the star, gas giants farther out, everything arranged on nearly circular and orderly orbits. But the universe simply does not agree. In only a tiny slice of the sky, the universe has already shown us gas giants orbiting closer to their stars than Mercury, planets as light as cotton candy, worlds darker than coal, and worlds bright as mirrors. It has created skies where iron falls as molten rain, where glass is ripped sideways through the atmosphere at supersonic speed. We once thought a planet needed a star to belong to, yet the universe has cast out rogue planets drifting alone through the void, cold and silent. Hundreds already seen and perhaps billions still hidden in the dark. Some of them even wander in pairs, orbiting one another without a single sun to warm them. We once believed a supernova would erase every nearby world, only to find planets around pulsars, as though even from the death of a star, second-generation planetary systems could still arise. We once assumed small stars could not produce giant planets. Yet TOI 6894b and LHS 3154b are there all the same, coldly denying that belief. The more exceptions appear, the clearer it becomes that they are no longer exceptions at all. Each new discovery strips away another layer of old confidence, revealing how many of our assumptions were built from exactly one sample, Earth and the solar system. But Earth is not the standard. It is only one possibility. The solar system is not the template. It is only one example among countless ways matter can arrange itself into worlds. Strange planets, then, are not meaningless outliers at the edge of the picture. They are the full range the universe is revealing, the true span of what is possible. The problem is that we have only seen what we are capable of seeing. Current technology is biased toward planets that are large, close to their stars, or pass directly in front of them from Earth's point of view. Small, rocky worlds on distant orbits almost disappear from observation. Planets around faint red dwarfs are still easily hidden within the limits of measurement. Objects that take decades to complete a single orbit around their stars simply have not given us enough time yet to reveal their patterns. That means the strangest part of the universe may still be waiting out of sight. When humanity begins to see smaller planets, more distant planets, and read their atmospheres in enough detail to track weather and chemistry almost in real time, it is very likely that new worlds will appear and shatter whatever remains of our theory. because that seems to be what the universe has always done. Find pathways we never imagined, configurations our models once dismissed as negligible or impossible. James Webb is opening that stage now. From dozens of light years away, it can still detect molecules that were once beyond reach, reconstruct temperature maps across planetary hemispheres, and identify chemicals that should not be able to coexist in the same atmosphere. And the next instruments, like the Extremely Large Telescope and the Habitable Worlds Observatory, will go even further, seeing smaller planets, reading atmospheres more deeply, and hunting for biosignatures with unprecedented precision. We may find signs of life, we may not, but either way, the answer will transform almost everything about how humanity understands its place in the universe. If we do, we will know that biology did not arise on just one planet. If we do not, we will understand that life may be so rare that Earth is more special than we had ever imagined. Either possibility is enough to make us humble, but even before we reach that answer, the search itself has already forced us to think beyond our Earth-shaped experience. Every strange planet pushes the boundary of the possible a little farther. Iron rain on WASP 76b, glass storms on HD 189733b, the darkness of TRES 2b, the blinding reflectivity of LTT 9779b, the crystallized carbon composition of 55 Cancri E, the cotton candy density of the worlds in Kepler 5.1, planets around pulsars, polar orbits, giant planets around stars so small they should not have had enough material to form them. Every one of those names once sounded impossible, until the moment it was confirmed. And each time, what truly collapsed was not the universe itself, but the feeling that our old rules had ever been enough. Because the universe does not care about the models humans use to make it feel familiar. It only operates according to what physics allows. And physics, it turns out, is far broader than our imagination. Planets can form in ways we did not foresee, pass through conditions we once called fatal, and survive in structures that older theories only knew how to dismiss. For billions of years, the universe has been experimenting with planetary systems with a patience humanity cannot match. And we have entered that story only within the last 3 decades, since the first confirmed exoplanets in 1992. Seen in that proportion, humanity is still almost like a cosmic child, only just learning to look beyond the cradle called the solar system, and only just beginning to understand that the rest of the galaxy is richer than anything we ever dared imagine. 30 years, on the timescale of the universe, is almost nothing, and yet in that brief span, humanity has found more than 6,000 worlds beyond the solar system, and each one has forced the old picture to stretch a little wider. I think the astonishing part is not the number itself, but the fact that from such a tiny sample, we have already encountered enough planets to make theory tremble. If our species lasts long enough to keep building telescopes, sharpening methods of observation, patiently reading data, and stubbornly asking questions, then in another 30 years, another century, or another 1,000 years, the very way we understand planets may look so different as to be almost unrecognizable. Those strange worlds out there are not merely discoveries. They are like doorways opening onto a universe far stranger than our first suspicions allowed. Windows into processes we still do not fully understand. Natural laboratories where physics operates under conditions Earth cannot hope to reproduce. But they do something else as well, something quieter and deeper. They reflect back upon our own solar system. Through those extreme worlds, we begin asking again whether Earth is truly normal, and whether the things once taken for granted in our own cosmic neighborhood are actually common at all. Each new discovery subtly shifts our sense of humanity's place in the universe, while at the same time unsettling planetary science, astronomy, physics, chemistry, and biology alike. Because the universe is not silent. It is speaking through wavelengths of light, through the faint wobble of distant stars, through the dimming that occurs when a planet passes in front of a star, through gravitational lensing, through the regular pulses of neutron stars. And humanity, in a very beautiful way, is learning how to listen. We are building better instruments, inventing better techniques, training new generations of astronomers to go deeper into the unknown. And the more clearly we hear, the more decisive the message becomes. The universe is larger than we thought, stranger than we imagined, more diverse than our models allow, and far more inventive than theory ever predicted. Perhaps that is why strange exoplanets no longer feel like exceptions at all. On the contrary, they are beginning to suggest that perhaps they are what is common, while Earth is the real difference. The solar system, with its stable, orderly, predictable structure, may not be the template, but only a rare case that had enough time to settle down. Most planetary systems may be more dynamic, more violent, always in a state of change. Planets migrate, orbits tilt, worlds collide, and others are flung out of their systems altogether. Some systems are still caught in the middle of that process now, like HR 5183b or TIC 241249530b, worlds whose orbits alone reveal histories of deep upheaval. The solar system today is peaceful because it is old. It has had billions of years to eject its troublemakers, round out its orbits, and ease itself into equilibrium. But it was not always like this. The early solar system saw migrations, major shifts in position, tilting axes, and heavy bombardments that left scars across the inner planets. We have simply arrived late enough to witness the quiet phase. In that sense, strange planets truly are time machines. They show us different slices of planetary evolution. Young systems reveal formation in progress, mature systems hint at stability and aging, and dying systems lay bare the unavoidable final chapter. WASP 1-2b is spiraling into its star. Pulsar planets orbit stellar corpses. Rogue planets drift masterless through the void. Each of those stages tells part of the cosmic story, where we came from, where we may be going, and what variations can happen in between. Even the future of our own solar system is faintly visible in these scenes. In about 5 billion years, the Sun will swell into a red giant, swallowing Mercury, Venus, and perhaps Earth. The outer planets, if they survive, will also be transformed by the heat of a dying star. After that, the Sun will cast off its outer layers and leave behind only a white dwarf core. At that point, any world still remaining will orbit a stellar remnant, and what is now our future is already the present of some systems we are observing today. But for now, we are still here, a thinking species standing on a small rocky planet, looking outward with eyes that are growing better and better, and continually meeting worlds that force everything that once seemed certain to begin shaking. What is precious in this is that the universe has no obligation to make itself easy to understand. It does not need to fit our assumptions, our models, or the drawers of classification we have built for it. It simply exists as it is. And science, in its most beautiful form, is not the art of confirming what we already believed, but the ongoing journey of being forced to revise those beliefs. Strange exoplanets are nature's clearest reminder that we still do not understand it all, that we must keep looking, keep asking, keep going farther. And humanity will do exactly that, because that may be our most persistent instinct. We explore, we question, we reach toward the unknown, even when it overwhelms us, even when it exposes our own limits. The strange planets we have found so far are only the prologue, a tiny sample of the immense diversity still hidden somewhere in the galaxy. Surely out there are worlds stranger than anything we have yet called bizarre, systems powerful enough to force textbooks to be rewritten, and the most basic assumptions about how reality works to be reconsidered from the ground up. And we will find them, because we have only just begun this expedition. The tools are being built, the methods are being refined. New scientists are growing up to continue into the darkness that earlier generations only just touched at the edge. What remains after all of this is perhaps not only the fact that the darkest worlds, the brightest worlds, the planets of iron rain, glass rain, diamond composition, wandering orphans, Worlds orbiting two stars, failed stars, dead stars, polar orbits, lopsided atmospheres, or impossible densities are all real. More important is that each such world stretches the boundary of the possible a little farther. They are like gifts the universe throws back to human curiosity, lessons in the creativity of nature, reminders that this cosmos is stranger than our ability to think it. So when we look up at the night sky, perhaps it is worth remembering that those points of light are not just stars. They are planetary systems, worlds turning in configurations we have only just begun to count. Some may be so strange they resist description. Others may be quiet, stable, more Earth-like, and perhaps even carrying life. Right now, we do not yet know which kind is more common, but we are moving closer to the answer. One discovery at a time, one strange exoplanet at a time, one moment of astonishment at a time. And each time it happens, humanity understands a little more clearly its place in this vast, radiant universe that always seems to know how to surprise us.